Okay, so I can show you here a microscope. It's an AFM, which is working in UHV, in ultra high vacuum, and it has a large scanner. So basically, you can also measure areas up to 100 by 100 micrometer, and by that you can also image cross sections from power devices, from real devices which are used in power electronics or in the industry. And the interesting thing is we measure here with the AFM tip, we measure the local concentration of dopants. So basically the tip scans across the surface about this cross section, and then you have areas where we have increased dopant concentration, or what we are interested in is really to measure these concentrations. And in that sense, it's also a bit in the direction that the AFM is not just a tool to measure topography, but it's something where we can basically also measure electrostatic forces. So it's a bit like a lab on a tip, so it measures forces, all kinds of forces, friction forces or electrostatic forces. In this case, electrostatic forces, and also we can measure basically local contact potential differences, which means basically that we use this Kelvin method, originally introduced by Lord Kelvin, to measure these local work function differences. I mean, that's something where we can get information about this dopant concentration. So this is quite a practical thing, not so much about the high resolution, but more about the dopant concentration, so something to get quantitative information. Okay, so we see insight into the vacuum system, and basically we can see here this large area scanner. So it's a closed loop scanner which moves in X and Y direction and also in Z direction, of course, and from top we get the AFM tip, which can be aligned relative to these areas of this power semiconductor devices. So we got the vibrations are much slower, and so we can do the experiments at a much lower vibration level. Okay, so we see here a low temperature microscope, which means it's running at 4 Kelvin, the temperature of liquid helium, and it is basically a microscope which is combined with an STM and an AFM. So basically you can measure both the forces and the current. The nice thing is, what we found out recently is that basically the resolution of AFM is now really getting better than STM. So you touch a CO molecule to the tip, so basically the tip is scanning the surface, and you touch to the CO molecule to the tip, and then the CO basically can touch the surface very closely to the surface and get into the repulsive regime. And by that you can basically get the highest resolution. So we can see, for example, nanoribbons with the resolution where you even can detect single hydrogen atoms, and also see the rings of the carbon. And in addition, and that's the most recent thing we did here, is also that we can move the ribbons across the surface and measure the lateral or the friction forces of these ribbons across the surface. So in that sense you can basically study friction, or in this case even the very low friction, also called superlubricity. So that's something which can be done with such a microscope. So it turned out that these graphene ribbons are sliding extremely well on gold, so they can move practically with nearly no force. So at room temperature they will already by thermal activation move around on the surface. Other than that, it's a microscope based on tuning fork. So it's a small tuning fork which you also use in Swiss watches, and that's the sensor basically. So it oscillates across above the surface, and you detect with this electronics here. You detect basically the frequency shift, and out of that you get the forces. So you can go down to a resolution of submolecular resolution. So you can see the rings of carbon, basically, for example, C60 or of these nanometers. So that's what you can do. Basically, the whole system here is a combination. On the right side here we have the preparation part. So here basically you can prepare the surface, you can evaporate some material, some molecules, you can anneal it and heat it, and then if it's prepared, basically it's transferred here with this transfer to the analytical chamber, and here this part here is actually the cryostat, which means you have this liquid helium bath, and attached to that you have basically the microscope. The microscope itself is not visible at the moment because it's measuring, so I will not touch it. But basically it's in here, so the real sense. So the tuning fork basically is in this part. You can manipulate it with this one, and also there's basically some optical access from the side.